Hey everyone, welcome back to my YouTube channel where we make engineering concepts simple and practical. But before we get hands-on with real-life examples, let's talk about something we usually don't even think twice about: the units we use every day. Have you ever wondered why we measure distance in meters, force in newtons, or sometimes in pounds? Well, today we're breaking down the systems of units, one of the essential building blocks of engineering mechanics. Before we dive in, make sure you've watched our previous discussion of the four fundamental concepts of mechanics: space, time, mass, and force. These concepts lay the foundation for everything we'll talk about today. Now, when we move from theory to actual measurement, we don't measure space directly. Instead, we measure space using length, like meters, feet, or miles. In mechanics, we group these measurable quantities, length, time, mass, and force, into what we call kinetic units. These are called kinetic units because they directly relate to motion, from the Greek word kinesis, meaning movement. They're the quantities used when applying Newton's laws, especially force equals mass times acceleration. In simple terms, they are the key players whenever we analyze motion, forces, and energy in mechanical systems. Among them, length, time, and mass are considered basic units, which we can define by standard references. But force is different. It's a derived unit that must always satisfy Newton's second law. And when all these kinetic units work together consistently under this law, we call it a consistent system of units. In engineering, we work with numbers all the time, but those numbers are only meaningful if we know the units we're working with. And globally, there are two major systems of measurement you'll often encounter: the International System of Units, or SI, and the US Customary Units. Alright, let's kick things off with the most widely used measurement system in science and engineering, the SI system. SI comes from the French term
Système international d'unité,
which means International System of Units. Let's take a closer look at the three basic units that make up the foundation of the SI system. First, length. Length is simply the measure of distance, how far apart 2 points are. It could be the width of a table, the height of a building, or the distance between two cities. In engineering and science, we usually express length in meters, but we also use multiples like kilometers for long distances, or submultiples like millimeters for tiny measurements. Second, mass. Now don't confuse mass with weight. They're not the same. Mass is the amount of matter in an object, basically how much stuff it contains. We usually measure mass in kilograms in engineering and science. Here's the key. A 10 kilograms object will still have 10 kilograms of mass, whether it's on Earth, the Moon, or floating in space. Why? Because mass doesn't change with location. But weight does. Weight is the force of gravity acting on that mass. So while your mass stays the same, your weight would be less on the Moon because of weaker gravity, and even zero in deep space where there's no gravity. And just like length, we can scale mass up with units like megagrams or down with grams and milligrams. Third, time. Time is all about measuring change, how long something takes to happen. From the blink of an eye to the ticking of a clock, everything we observe in mechanics happens over time. In the SI system, the second is the basic unit. We also scale time up or down. Milliseconds for things that happen super fast. Minutes, hours, days, months, or years for longer periods. Pretty simple, right? Now, here's something a lot of people don't realize. The units we use every day aren't just random guesses or old traditions passed down. They're actually based on highly precise scientific standards, carefully defined by international agreement. Let's start with time. You might think a second is just, well, a second, but it's actually defined using atomic physics. The second was first defined as 1/86,400 of a mean solar day. That's 1 second out of a full day. But today, it's officially based on the 9,192,631,770 vibrations of a cesium-133 atom during a specific energy transition. Crazy, right? Instead of relying on clocks, we now rely on atomic vibrations. That's why atomic clocks are the most accurate in the world. Next, length. Way back, a meter is originally defined as 1/10,000,000th of the distance from the equator to either pole. But as science advanced, we needed something much more precise. So now, the meter used to be defined as 1,650,763.73 wavelengths of a specific orange-red light emitted by krypton 86 during a certain atomic transition. Basically, it's tied to the exact color of light a krypton atom gives off, and with lasers and spectroscopy, we can measure it with incredible accuracy. Finally, mass. You might find this cool, or a little weird. The kilogram, roughly the mass of 1 liter or 0.001 cubic meter of water, is literally a platinum iridium cylinder kept at the International Bureau of Weights and Measures in Sèvres, France. For more than a century, the entire world measured mass based on a single object, Legrand K, or officially, the international prototype of the kilogram. But here's something fascinating. The man behind the drive for a standardized system of measurements, including the kilogram, was Gabriel Mouton, a French scientist from the 1600s, often called the father of the metric system. However, it wasn't until the late 18th century that French revolutionaries pushed for a universal system based on natural constants, with scientists like Jean-Charles de Bourda and Joseph-Louis Lagrange leading the charge. Fast forward to the 19th century, and that's when the international prototype kilogram, Legrand K, was created. But here's the problem. Even though it was handled with extreme care, tiny changes still happened over time, like gaining or losing atoms, which meant the definition of a kilogram wasn't perfectly stable. That pushed scientists to search for something better, something constant, and that's when Planck's constant came into the picture. So who's behind this? It's named after Max Planck, a German theoretical physicist often called the father of quantum theory. In 1900, Planck introduced his famous constant while studying black-body radiation, and this became a fundamental value in quantum mechanics. Fast forward to 2019, the kilogram was officially redefined using Planck's constant, thanks to precision instruments like the Kibble balance, invented by Brian Peter Kibble. Now, instead of relying on a physical object, we define mass based on a fixed universal constant tied to the laws of physics. So from a simple metal cylinder to the cutting edge of quantum physics. That's how we measure mass today. But how does the Kibble balance work? We'll save that for another video. So when you use seconds, meters, or kilograms, you're actually using units tied to universal physical constants, which means they're the same for everyone, everywhere, all the time. And that's what makes the SI system so reliable and powerful in engineering, science, and everyday life. Now, when we talk about force in the SI system, we don't treat it as a basic unit like length, mass, or time. Instead, force is what we call a derived unit, meaning it comes from combining the basic units according to a physical law. And that law? You probably know it. Newton's second law of motion. Force equals mass times acceleration. So, in the SI system, the unit of force is named after the man himself, Sir Isaac Newton. Here's how it works. If you apply a force to a 1 kilogram object, and that force makes it accelerate at 1 meter per second squared, then you are applying exactly 1 Newton of force. In equation form, 1 Newton is equal to 1 kilogram times 1 meter per second squared. That's why the Newton is written in terms of kilograms, meters, and seconds. It literally ties together mass, length, and time, showing how much force is needed to move an object. And this is what makes the SI system consistent and reliable. Every time you calculate force in SI, you're working with units that all fit perfectly within Newton's second law. Now let's talk about something a lot of people mix up: weight and mass. In physics, weight is the force of gravity acting on a body. And since weight is a force, it should always be measured in newtons, not kilograms. Let's see how that works with a simple example. If you have a mass of 1 kilogram, how much does it weigh on Earth? From the formula, weight is equal to mass times acceleration due to gravity. So that's weight equals 1 kilogram times 9.81 meters per second squared. Then simplify, we get weight equals 9.81 newtons. So remember, mass tells you how much stuff an object has. But weight tells you how hard gravity is pulling on it. And in physics, weight equals force equals newtons. So why is the SI system so important? It's what we call an absolute system of units. That means these units don't change no matter where you are. You could be in Manila, anywhere in the Philippines, in another country, on the other side of the Earth, or even on another planet, and a kilogram is still a kilogram, a meter is still a meter. That's the power of the SI system, universal, consistent, and built for precision. Now, one of the best things about working with the SI system is how easy it is to handle really big or really small numbers. Thanks to prefixes. Prefixes help you avoid writing a long string of zeros by giving numbers a clear, compact form. Here are some of the most common ones you'll see in engineering. Kilo with the symbol small letter K means 1,000, or 10 to the power of 3. Milli with the symbol small letter M means 1,000th, or 10 to the power of negative 3. And mega, with the symbol capital letter M, means 1 million, or 10 to the power of 6. Here are some quick examples and their symbols. 1 kilometer equals 1,000 meters. 1 megagram equals 1,000 kilograms. Note that 1 megagram is also known as a metric ton. 1 kilonewton equals 1,000 newtons. 1 millimeter equals 0.001 meter. 1 gram equals 0.001 kilogram. So instead of writing 3,820 meters, you can simply say 3.82 kilometers. It's way easier to read and work with. When it comes to time, though, 1 minute equals 60 seconds. 1 hour equals 3,600 seconds. Just a reminder, time conversions aren't based on powers of 10. So be extra careful when converting time units. And by the way, here's the SI prefix table on the screen, complete with their symbols. Feel free to pause the video and take note. Let's start with the bigger measurements. Queta, that's a capital letter Q, which means 10 to the power of 30. Rana, that's a capital letter R, which means 10 to the power of 27. Yoda, that's a capital letter Y, which means 10 to the power of 24. Zeta, that's a capital letter Z, which means 10 to the power of 21. Exa, that's a capital letter E, which means 10 to the power of 18. Peta, that's a capital letter P, which means 10 to the power of 15. Tera, that's a capital letter T, which means 10 to the power of 12. Giga, that's a capital letter G, which means 10 to the power of 9. Mega, that's a capital letter M, which means 10 to the power of 6. Kilo, that's a small letter K, which means 10 to the power of 3. Hecto, that's a small letter H, which means 10 to the power of 2. Deca, that's small letters D and A, which means 10 to the power of 1. Take note that both deca with a letter K and deca with a letter C mean the same thing, but the correct SI spelling is deca with a letter C. Deca with a letter K is a variant spelling used in some countries, but deca with a letter C is the official form in the International System of Units. And this part is for the standard units, such as Kelvin for temperature, meter for distance or length, ampere for electric current, second for time, mole for the amount of substance, gram for mass, candela for the intensity of light, and others. Now for the smaller measurements. Deci, that's a small letter D, which means 10 to the power of negative 1. Centi, that's a small letter C, which means 10 to the power of negative 2. Milli, that's a small letter M, which means 10 to the power of negative 3. Micro, that's the Greek letter lowercase mu, which means 10 to the power of negative 6. Nano, that's a small letter N, which means 10 to the power of negative 9. Pico, that's a small letter P, which means 10 to the power of negative 12. Femto, that's a small letter F, which means 10 to the power of negative 15. Atto, That's a small letter A, which means 10 to the power of negative 18. Zepto. That's a small letter Z, which means 10 to the power of negative 21. Yocto. That's a small letter Y, which means 10 to the power of negative 24. Ronto. That's a small letter R, which means 10 to the power of negative 27. Quecto. That's a small letter Q, which means 10 to the power of negative 30. Here's how they look when used with the meter as the basic unit or standard unit of length in the SI system. Also, take note of the pronunciation, because some prefixes are pronounced differently or have a different stress when spoken. 1 quintameter, 1 ronometer, 1 yotometer, 1 zetameter, 1 hexameter, 1 pentameter, 1 terameter, 1 gigameter, 1 megameter, 1 kilometer, 1 hectometer, 1 decameter, 1 meter, 1 decimeter, 1 centimeter, 1 millimeter, 1 micrometer, 1 nanometer, 1 picometer, 1 femtometer, 1 attometer, 1 zeptometer, 1 yoctometer, 1 rontometer, 1 quectometer. But here's something you need to watch out for. These prefixes only work this way if you're using the meter as the base unit for length. If you replace meter with another standard unit, like gram for mass, second for time, Kelvin for temperature, ampere for electric current, mole for amount of substance, or candela for luminous intensity, the meaning of the prefix changes depending on what quantity you're measuring. Now, these are some units that you'll often see with prefixes, while others you might not encounter as often with prefixes. Feel free to pause the video and take note. For the SI-derived units with prefixes allowed: Hertz, Newton, Pascal, Joule, Watt, Coulomb, Volt, Ohm, Siemens, Farad, Henry, Weber, Tesla, Lumen, Lux, Gray, Sievert, Becquerel, and Catal. For the information units, non-SI but accepted: bit and byte. For the supplementary/geometrical units: radian and steradian. Then, these are units that usually do not take prefixes: degree Celsius, but you can prefix Kelvin. For time units like minutes, hours, non-SI, prefixes not standard. Liter is allowed, but liter is not SI, commonly used with prefixes though. You don't have to memorize every single prefix, but it really helps to know the most common ones and their symbols, especially when you're solving engineering problems. Here are the most commonly used SI prefixes: kilo, mega, giga, milli, micro, nano, and centi, but prefix centi is common in measurements like centimeters. One more thing. Certain prefixes like hecto, deca, deci, and centi are generally avoided in engineering, except when you're dealing with areas, volumes, or when using centimeters for non-technical purposes, like body measurements or clothing sizes. For example, let's say you're measuring force. It's correct to say 5 kilonewtons instead of 5,000 newtons. But it's not proper to say 5 centinewtons or 5 decanewtons. Those prefixes are not commonly used in engineering calculations. Another example of length: you'd say 50 millimeters for a small measurement. But you wouldn't typically say 50 decimeters instead of 5 meters. That's rarely acceptable in engineering. Now, why does this matter? Because using the right multiple or submultiple makes your numbers easier to write, read, and work with. Another examples: it's simpler to write 427.2 kilometers instead of 427,200 meters. Or to write 2.16 millimeters instead of 0.00216 meters. And here's a pro tip. Whenever you're writing numbers in SI units and you've got more than 4 digits on either side of the decimal point, always use spaces, not commas, to group digits into threes. For example, 427,200 meters, using space, not 427,200 meters with a comma. 0.002 space 16 meter, not 0.002 comma 16 meter. Funny enough, that's not how my grade school teachers taught it. Kinda weird realizing that now. Why is this so? Because in many countries, like Germany, France, Italy, and other parts of Europe, commas are actually used as decimal points, and we want to avoid that confusion. And if you're taking AutoCAD classes, you'll notice this too. Sometimes measurements show commas instead of decimal points. That's why you should always double-check your units and settings, so you don't end up with the wrong values in your drawings. However, if you're unsure about notation, pronunciation, or formatting standards, always check with your instructor, professor, or workplace guidelines. It's better to ask than assume, especially when it comes to engineering standards. So, correct prefixes plus clear number formatting equals clean and professional engineering work. Now let's talk about what happens when we square or cube measurements. When you measure a surface, like the area of a floor or a wall, you're working with square units. That's why we express area in square meters. For example, a square that's 1 meter on each side has an area of 1 square meter. For volume, like the space inside a box or a container, we use cubic meters. That's because volume measures length times width times height. For example, a cube that's 1 meter on each side has a volume of 1 cubic meter. And just like with basic units, prefixes apply here too, but with a twist. When you square or cube a length unit with a prefix, the power applies to the prefix as well. Now let's try a sample conversion for area. Let's convert 1 square centimeter to square meters. We already know that 1 centimeter is equal to 0.01 meter, or, in powers of 10, that's 10 to the power of negative 2 meters. But since we're dealing with square centimeters, we need to square the whole thing, and that includes both the number and the unit. Remember the power of a product property? It says when you multiply numbers or variables inside parentheses and raise them to a power, you distribute the exponent to each factor inside. So when we square 0.01 meter, it becomes 0.01 squared times meter squared. Now what's 0.01 squared? That's 0.0001, and the unit becomes meter to the power of 2. So we write it as 1 centimeter squared is equal to quantity 0.01 meter squared is equal to 0.0001 meter squared. Or, if we use scientific notation, which we'll talk about more in a separate video, that's 1 centimeter squared is equal to 10 to the power of negative 4 meters squared. That's how you convert square centimeters to square meters. Don't forget to apply the exponent to both the number and the unit. Let's now try it with volume. We'll convert 1 cubic centimeter into cubic meters. We know that 1 centimeter is equal to 0.01 meter, or 10 to the power of negative 2 meters. But since we're dealing with cubic centimeters, we're raising everything to the power of 3. And just like before, that exponent applies to both the number and the unit. So it looks like this. Quantity 0.01 meter raised to the power of 3 is equal to quantity 0.01 raised to the power of 3 times meter raised to the power of 3. Now what's 0.01 raised to the power of 3? That's 0.000001, or 10 to the power of negative 6. So we write 1 centimeter raised to the power of 3 is equal to quantity 0.01 meter raised to the power of 3 is equal to 0.000001 meter raised to the power of 3, or in scientific notation, that is equal to 10 raised to the power of negative 6 meter raised to the power of 3. Again, same idea. Apply the exponent to both the number and the unit. Simple, right? Here's a fun fact you'll actually use, especially when dealing with liquids. 1 liter is exactly the same as 1 cubic decimeter. That's right, a liter is just a fancy way of saying 1 cubic decimeter. And here's another one you'll want to remember. 1,000 liters is equal to 1 cubic meter. So the next time you see 1 cubic meter, just think of it as 1,000 liters of space, whether it's water, fuel, or any liquid. Simple conversions, but super useful in real life. Now here's a golden rule for derived units, and this one's important for engineering work. When you're working with derived SI units, especially when one unit is divided by another, you're allowed to use a prefix in the numerator, but never in the denominator. For example, imagine you have a spring that stretches 20 millimeters when you apply a force of 100 newtons. The spring constant K is calculated like this. Spring constant K is equal to 100 newtons over 20 millimeters. But hold on, you can't leave it like that. We have to convert millimeters into meters first. We know that 20 millimeters is equal to 0.020 meter. So now, spring constant is equal to 100 newtons per 0.020 meter. Simplify 100 divided by 0.020, we get 5,000 newtons per meter. Or, if you want to simplify with a prefix in the numerator, spring constant is equal to 5 kilonewtons per meter. That's correct. But you should never write it as 5 newtons per millimeter, even if the math seems easier. That breaks the SI unit rule. And if you want a quick summary, take a look at this table of the principal SI units used in mechanics. It shows the quantity, the SI unit, its symbol, and the formula where it's usually applied. As we go along this lecture series, you'll encounter these units again and again in different formulas, examples, and problems. Feel free to pause the video or screenshot it for quick reference. Now, let's cross over to the U.S. customary units, still common in American engineering, especially in construction and manufacturing, for the length, time, mass, and force. First, let's talk about length in the U.S. customary system. In this system, length is measured in feet. The symbol is FT. Quick reminder, foot is singular, like 1 foot, whereas feet is plural, like 3 feet. But have you ever wondered why it's called feet or foot? Well, it actually comes from the length of a human foot. Back in ancient times, people used body parts like the foot, hand, or thumb to measure things. Eventually, rulers like England's King Henry I set official standards, and over time, the foot became fixed at 0.3048 meter, based on the metric system for accuracy. So even though Americans use feet, inches, and miles, they're still connected to the meter behind the scenes for precision. And here's a quick recap of other U.S. customary length units. 1 inch is equal to 1/12 of a foot. And 1 mile is equal to 5,280 feet. Now, speaking of miles, let's clear this up. The statute mile, used on land, equals 5,280 feet. This was set by law in England back in 1593, and it's the mile you use for road distances. The nautical mile, on the other hand, is used at sea and in aviation, and is based on the Earth's curvature. It equals 6,076.12 feet, which is exactly 1 minute of latitude. So, if you're measuring land distance, 1 mile is equal to 5,280 feet. That's the statute mile. If you're sailing or flying, 1 nautical mile is equal to 6,076.12 feet. Crazy how these old measurements evolved, right? From human footsteps to global engineering standards. Now, let's talk about force. In the U.S. customary system, the basic unit of force is the pound, written as lb. But wait, why lb and not pd, or something that actually makes sense? I wish it was pd, but hey, I'm just kidding. That comes from the Latin word libra, which means balance or scales. The full term libra pondo actually meant a pound by weight in ancient Rome. Over time, we kept lb as the abbreviation for pound, even though we dropped the Latin. So yes, when you see lb, remember you're looking at a little piece of Roman history in your engineering problems. Pretty cool, right? Engineering even has its own secret language based on history. Let's clear up a common confusion when solving engineering problems with US units. You've probably heard of the pound as a unit of mass, and that's totally fine for everyday use, especially in business and commerce. But in engineering and physics, that's a different story. We can't use the pound as a unit of mass in computations, because it wouldn't match the system of base units we're working with, like feet, seconds, and pounds force. Here's why. When you apply a force of 1 pound to a standard object, it doesn't accelerate at 1 foot per second squared. It accelerates at 32.2 feet per second squared, thanks to gravity. But according to Newton's second law, if a force of 1 pound is applied, and we want the object to accelerate at 1 foot per second squared, its mass should be what? Force equals mass times acceleration. So, force of 1 pound equals mass times acceleration of 1 foot per second squared. So solving for mass, we get mass equals 1 pound per 1 foot per second squared. Simplify, we get 1 pound second squared per foot. This special unit of mass is called the slug. No, not that one. Yes, you heard that right. Slug. And yes, the slug is 100% a real unit in engineering. The term slug actually comes from Old English, meaning a solid lump or a heavy piece of metal. And just like that, a slug in physics means something with serious heft, not your garden variety slime friend. And here's the kicker. A slug is about 32.2 times heavier than a pound of mass. In statics, where we mostly deal with forces and weights, it's fine to work with pounds. But in dynamics, when you're dealing with forces, masses, and acceleration, you'll need to express mass in slugs if your weight is in pounds. Mass equals weight divided by acceleration due to gravity, where acceleration due to gravity is equal to 32.2 feet per second squared. So next time you see a problem involving motion, remember pounds measure force, but slugs measure mass. But here's a common source of confusion you need to watch out for. lb sub f means pound force. That's force, which depends on gravity. lb sub m means pound mass. That's the amount of matter, like how much stuff is in an object. Be careful. In practice, people often say pound, without specifying if they mean lb sub f or lb sub m, which can lead to confusion. Here's the relationship. 1 lb sub f equals 1 lb sub m times 32.2 feet per second squared. Or simply, 1 lb sub f equals 1 lb sub m times g, where g is the standard acceleration due to gravity, approximately equal to 32.2 feet per second squared. So if you want to convert mass to force, multiply the mass in lb sub m by g and divide by g if you need the other way around. But before we move on, let's clear up a common misconception. You've probably heard of imperial units, right? People often think they're the same as US customary units, but they're actually not identical. The imperial system came from Britain in 1824, after the US had already adopted its own customary measures. The US customary system dates back to colonial America, and while both systems use similar names like inches, feet, and pounds, their values differ in some cases. For example, 1 imperial gallon is equal to 4.546 liters, whereas 1 US gallon is equal to 3.785 liters. And here are more key differences between the imperial system and the US customary system. Feel free to pause the video and take note. So, while they look alike, they aren't interchangeable, especially in engineering calculations. So, next time someone says imperial, you'll know the difference. Finally, time. Now you might wonder, why is time the same in both SI and US systems? Simple, because time is a universal constant. Wherever you are in the world, a second is always defined the same. It's the time it takes for a cesium-133 atom to vibrate exactly 9,192,631,770 times. That's why both systems, metric or customary, use the second as the base unit of time. So whether you're solving problems in meters and newtons, or feet and pounds, time stays the same, because physics doesn't change across borders. Now, if you're working with US customary units, here's a heads up. Conversions aren't always as straightforward as with SI units. They need a little more attention. Let me show you an example you'll probably encounter. How do you convert 30 miles per hour into feet per second? Step 1. Write your given speed. 30 miles per hour. Now, we want feet per second, so we'll use conversion factors that cancel out miles and hours. Again, here's something important to remember. When we use 1 mile equals 5,280 feet, we're talking about statute miles. That's for land distances. We're not dealing with nautical miles here, for now. So our conversion goes like this. 30 miles per hour times in 1 mile, that is equal to 5,280 feet, times in 1 hour, that is equal to 3,600 seconds. Breaking it down, miles cancel out, hours cancel out. Now multiply the numbers. 30 times 5,280 divided by 3,600, and that is equal to 44 feet per second. So 30 miles per hour equals 44 feet per second. The big takeaway: always know which units you're using, cancel them step by step, and don't rush your conversions. Because whether you're dealing with land speed, air speed, or seafaring distances, using the right conversion factor is everything. And believe it or not, a lot of engineering students get the wrong answers, not because they don't know the topic, but because they're not paying close attention to what's being asked, or what units they're supposed to give in the final answer. Please refer to the following table for the commonly used U.S. customary units. Feel free to pause the video or screenshot it for quick reference. To wrap up today's lesson on systems of units, here's the main idea you need to take with you. SI units. These are absolute, universal, and the standard for global engineering. They don't depend on location or gravity, which makes them perfect for scientific and technical work worldwide. Meters, kilograms, seconds, and newtons all work consistently, whether you're in the Philippines, the US, or even on Mars. US customary units. Still widely used, especially in the United States, but remember, this system is gravity-based, meaning its force units are tied to Earth's gravitational pull. Plus, unit conversions in this system are a bit more tedious and prone to mistakes if you're not careful. And most importantly, always double-check your units in every calculation. It might seem basic, but wrong units can totally mess up your answer, your design, or worse, your entire project. Unit consistency isn't just a classroom lesson, it's an everyday engineering habit. So remember, when it comes to engineering, the right formula means nothing if your units don't match up. Master the units and you're halfway to mastering the problem. If you find this video helpful, hit that like button, subscribe for more engineering insights, and drop your questions in the comments below. And don't miss our next topic, where we'll tackle something every engineer needs to know: conversion between SI and US customary units. See you in the next one. Bye.